And now to the business of the day. And without further ado, I call to the podium our chair of the day, Peter Addison, to take over today's meeting. Thank you.
Thank you very much, President Adrian. We are indeed very fortunate today to have two speakers from WEHI, and we've been involved with WEHI in a sense of making contributions for a few years now. So it's going to be very interesting to hear a little bit more about WEHI. So I'll shortly introduce Professor Doug Hilton, but just to give you a bit of background on WEHI, established in 1915, Australia's oldest and longest serving medical research institute for more than 100 years. WEHI researchers have been making transformative discoveries in cancers, infectious and immune diseases, developmental disorders and healthy aging, leveraging cutting-edge technologies and highly collaborative networks. WEHI brings together multidisciplinary teams comprising world-leading experts from a range of diverse scientific disciplines, all committing to creating a brighter, healthier future for all. So just by way of background, now I will introduce Doug Hilton, and then I'll
people in the community that are supportive of what we do is a huge boost to our enthusiasm. It gives us the resilience and it allows us to tackle difficult problems for a long period. So I'm really delighted that we can talk to you today. I extend an invitation to all of you to visit WEHI. WEHI is your institution. It's part of the community, part of civil society. I would love for you to come in, lift up our bonnet and have a look at the engine of research that is underneath. You can talk to Ava about a visit if you're interested, and we have update in our newsletter on the table. I encourage you to take one of those home and read it over a cup of tea tomorrow at breakfast. And I do want to apologise because we have a 1:30, 2 o'clock meeting of the NHMRC that is talking about really creative changes in the way we fund research and become more inclusive. And certainly diversity and inclusion has been a passion for me in the last few years. So I apologise for having to dash off as I leave the stage, and thank you for the opportunity for us to be able to present to you.
Well, thank you very much, Doug, for your most informative talk. I think we all know the name WEHI, but perhaps don't fully understand the role that they play. So they're a leading organisation, obviously, with a lot of these diseases and making great inroads. So I'd now like to introduce our second speaker, Dr. Danushka Marapana, and he is currently a senior research officer at WEHI, working with Professor Alan Cowman's team studying malaria, a parasitic disease that is responsible for more than 620,000 deaths each year, and that's a large number, mostly in children under the age of 5. Dr. Marapana completed a Bachelor of Biomedical Science, Microbiology and Immunology at the University of Melbourne and a PhD at WEHI. His current research aims to advance the understanding of how malaria-causing parasites infect and cause disease in human cells. Recently, new parasite strains emerged that are resistant to available drugs. His research aims to develop new methods of killing these drug-resistant parasites. Ultimately, the hope is that this will help us develop new anti-malarial treatments that will help to overcome the emerging drug-resistant problem. So I now hand over to Danushka. Thank you.
Yes, that would be great.
Sorry, I'm just going to test that this works. Yep, excellent. So thank you so much for the opportunity for us to come in from Weehai and talk to you. It's been a really wonderful experience. I've really enjoyed being at our table and hearing what the Rotarians have done over these last many years. I've got to say it's been a completely eye-opening experience for me. So my name is Danushka, and I'm a postdoctoral fellow at the Walter and Eliza Hall Institute. So I specifically work in the Division of Infectious Disease and Immune Defense, and I'm a molecular biologist. So we work on what is arguably the most deadliest parasite in the world, and that comes from a species, a genus known as Plasmodium, and it's the parasite that causes human malaria. All right. So I really like this slide as an introduction into what malaria is. It's not? Oh, no. Yeah, that's all right. Would you like me to keep talking? That's fine. All right. So there are 6 kinds of malaria parasites that infect humans. And the video that you would have seen was of the most infectious of them, the deadliest of them, called Plasmodium falciparum. And the parasite causes disease by infecting human red blood cells. So the video was of a microscopy team who've taken a live imaging of how the parasite actually gets inside the red blood cell. All right. So malaria is a really ancient disease, as you might know. It's been with humanity as long as there's been humanity. So it's changed the dynamics of not just our civilization, but even of us. So we've got evidence of malaria since the Mesopotamian region. We've seen evidence that King Tutankhamun, when he was exhumed, he had not just one malaria parasite infection in his body, he had several. So malaria was quite a big deal at that time too. We've got evidence from the Indian Vedas from about 1500 BC. We've got evidence from the ancient Chinese medical texts that talk about malaria disease, and they also talk about how malaria could be cured. That's as far back as the ancient Chinese empires. We've also got mentions of malaria disease in the Iliad. We've got mentions of it from Aristotle and Plato. And there's real speculation that malaria might have been one of the causative agents for the fall of the Roman Empire, in that it weakened the Roman army so much that the barbarians were then able to invade, to overcome them much easier. In the 20th century, it's estimated that malaria may have caused between 150 and 300 million deaths. That's about 2 to 5% of all deaths in that century. So malaria, it's in the early 1800s, it wasn't really known what caused malaria. It was just thought to be bad air. So the name malaria actually comes from the Italian for bad air. And then we've got, So then in the later 1800s, a person called Alphonse Laveran took a look down the microscope, and he was able to see these tiny malaria parasites hiding inside red blood cells that were eating the red blood cells from the inside out. And for this discovery of the malaria parasite, he received the Nobel Prize in 1907. And around the same time, the discovery of the mosquito vector that carried it was identified by Ronald Ross. So now we've got information of the parasite that caused the disease, and we've got the vector that carries the parasite to cause disease in humans. So how does the disease happen? So we've got a mosquito that carries the parasite that bites us. And then the mosquito, as it bites us, it's there to take up some blood from us. So its primary aim isn't to actually inject parasites into us. But in order to bite us sufficiently long enough to get a blood meal, it needs to make sure our blood stops clotting. So what it does is it injects anti-clotting factors from its saliva into the injection site. And as it does so, it also injects the parasites that are in its salivary glands. So that's how the malaria parasite gets into our skin. And after about half an hour, the parasites that are just in and under the skin make its way into a blood vessel. And then once it enters a blood vessel, that blood vessel takes the parasite all the way into the liver. And this is where the first round of infections start. So the parasite enters the liver cell, stays in there for about 7 days, and a remarkable transformation happens. So that one parasite over 7 days becomes 10,000 parasites. And then the parasite bursts out of the liver cell. It's called a hepatocyte. Once it bursts out, that's the most deadly stage of the infection, because the parasite that burst out, they can't infect liver cells anymore. They can only infect human red blood cells. And it's the red blood cell stage of infection that kills us. So the parasites enter our red blood cells and they grow inside it and they eat away at the hemoglobin that's inside the red blood cell. You may have heard of hemoglobin. It's how our red cells carry oxygen. So once it eats up all the hemoglobin, the red cell is effectively dead and the parasite grows inside it. That one parasite that went in now becomes 32 parasites. And it bursts out of the red cell and starts reinfecting more and more and more red cells. So this happens, so the period of a red cell infection lasts about 48 hours before the parasite bursts out and is able to infect more red cells. So at this stage of the infection, you can have as many as 1 trillion parasites inside your body. And so this is the symptomatic stage of the disease. This is the stage for which we give medicines. And so all of the symptoms that you associate with malaria, you have your fever, you have your chills, you have your headache, they all happen in the blood stage. And sorry, just give me a sec. Yeah, so they all happen in the blood stage. And so we would like to create medicines that can target this blood stage. So what's the status of malaria right now in the world? So we've got about 220 million infections last year, and those number of infections have gone up considerably because of COVID. And most of these infections happen in Africa. So Africa bears the brunt for both the infections, the infection risk, as well as all of the deaths of malaria. So malaria is quite a cruel disease in that the fraction of the population that it targets is actually young children. So children under the age of 5, about 60% of the victims of malaria are children under the age of 5. And that hasn't changed over the last 20 years, to be honest. It's been right around the 60% mark. So I'd like to tell you what we do at WeHi over the last 20 years. I haven't been at WeHi for 20 years, but over the last 20 years, I'd like to tell you what we've done. So since the early 2000s, we've looked at how the parasites enter our red blood cells. And so we've identified some really critical proteins that the parasite makes. So these proteins are these exquisite molecular machines that come together to form what looks like a key for the entry of the parasite into the red blood cell. So the idea is that we can create drugs and we can create antibodies that block these proteins so that the parasite can't enter the red blood cell anymore. So it doesn't enter the red blood cell, no more infection. Another research program we've got at WeHi is to kill the parasite whilst it's inside the red blood cell. So we do this in one of 2 ways. Firstly, we know that the parasite, when it enters the red blood cell, needs to modify it. It needs to change the architecture of the red blood cell in order to survive. And we've identified this single conductor protein that does the entire job. So we've even got the shape of it, and WeHi chemists have created a drug that binds perfectly inside this one protein that the parasite makes. And so is able to kill the parasite whilst it's still inside the red blood cell. So this is a research program that started in 2002 and just saw, the drug was created about 2 years ago. And the most exciting bit of new information that's come out from WeHi is the development of a new drug in collaboration with the pharmaceutical company Merck. So it's a compound called WeHi 382. They've given it a fancy name. So WeHi 382 is a drug that kills the parasites before it can leave the red blood cell. So I've told you that the parasite needs to get into the red blood cell, grow inside it, and then get out. So this drug stops them from getting out of the red blood cell, but it even kills the parasite at other stages. So it kills the parasite inside the mosquito, and it kills the parasite inside the liver stage. And we've got the shape of this protein as well through a technique called structural biology. And we've got the shape of that protein that the drug targets. And we've got the actual drug stuck inside this beautiful groove that blocks this protein from working. So the really amazing thing about WeHi 382 is that most drugs tend to only target one protein. And that's how drugs work. They block the function of one protein by binding to it. But WEHI-382 is really special. It targets two proteins at once. And so WEHI-382 is the first drug that we've seen for a long time for which parasites don't get any kind of resistance. We can't find resistant parasites to WEHI-382. And so this drug is now progressing through safety trials before it goes into preclinical testing, and then hopefully it'll get out into the market as a true antimalarial. All right, so I just mentioned resistance. So why is resistance so important? So it's a reason why we can't get rid of malaria. So it looks like most of the resistance that we see is for best-in-class antimalarials. So we've got antimalarials since the 1950s, but our parasites rapidly develop resistance to them. So we've got the other interesting thing is that most of the resistance that we see seems to originate in Southeast Asia. So we've got the greater Mekong subregion that contains Thailand, Cambodia, Myanmar, and Laos. And so the resistance seems to originate in parasites that come from that region, and then it can spread to Africa. And Africa is the hotbed. You don't want drug-resistant malaria getting in there, because that's where we get most of the burden of infection. That's where we get most of the burden of death. So we need to stop it before it gets to that point. So I'd like to tell you how drug resistance arises. So when we take any drug into our body, our cells get to see those drugs. And our cells, the DNA in our cells makes protein. And the drug that we take goes and binds the protein in our cell against which it was designed. That's just how drugs work. And so if the protein is really critical for the survival of that cell, then that cell is killed. But you can have resistance because the DNA in our cells, in every one of our cells, keeps changing all the time. It changes very subtly, but sometimes that DNA change is enough to change the shape of that particular protein. And if the shape change is sufficient, our drug will not bind that protein anymore. And now that cell is able to survive because the protein has changed its shape. Sometimes the DNA changes so much that rather than having just one copy of a protein in a cell, you can have multiple copies. You can have hundreds of copies inside a cell. And then when you add the drug, because you don't have sufficient drug to mop up all of that excess protein, you're going to end up having some protein that can still do its job. So that's the second way we get resistance. So we can get resistance either through a subtle shape change, or we can get resistance because of what we call an over-amplification of a protein. And so the issue that we have is that half of the world is at risk of malaria. And the risk is getting compounded because of the presence of drug-resistant parasites. So the way we'd like to go about addressing this is to resensitize our parasites, our drug-resistant parasites, to the original antimalarial drugs. So how can we do this? And so there's this wonderful technique that's come out of the cancer field called a PROTAC. So a PROTAC stands for a proteolysis targeting chimera. It's a really big word, but I'll shorten it down for you. It just means that it's a degrader. So the PROTACs work rather than by blocking a protein, it destroys it. And so how does that work? So before I can tell you that, we need to know how proteins live and die. So a protein gets made in a cell from our DNA, but how does it die? So we've got proteins that just tend to accumulate in our bodies. And then at a certain point, it's got to be given a death signal. And that happens from a protein that we produce in our own cells, and the parasite also produces in its cells, called a tagger. And what the tagger does is it just goes and touches the protein that's meant to be destroyed, and it transfers a tag onto it. This tag, we call this tag a ubiquitin tag, but effectively what it is a death tag. It tells the cell, and it specifically tells the cell's shredder machinery called a proteasome that this protein is destined to be destroyed. And so the proteasome recognizes this tag and it destroys it. It shreds it to pieces. So what we'd like to do with PROTACs is exactly the same thing. We would like to go and destroy our parasite proteins using parasite taggers. And so that's what we'd like to do with a PROTAC. So a PROTAC isn't just one isn't a drug with just one function. It's a drug with two functions. So effectively, it's got two arms. One arm will go and bind your protein, your really bad protein, let's say in the parasite, the protein that's causing the disease. And the other arm will go and bind a tagger from the parasite. So the PROTAC is meant to bring the tagger close enough to our target so that it touches it, it tags it, and then it sends it away for destruction. So what's the advantage of a PROTAC over just a normal standard drug? So like I said, in normal wild type, in normal cells, when we have our protein, we can, normal drugs would just stop that protein's action by binding it and stopping it from working, whereas a PROTAC will bind this protein and then destroy it. And unlike traditional drugs, PROTACs can bind are two kinds of mutations that we see in cells. It can bind the subtly shape-shifted protein as well as the overexpressed protein and send them to be destroyed by the cell's shredder. So the other wonderful thing about a PROTAC is that it works in an iterative fashion. So it can destroy, oh, I'm sorry, I didn't realize I was back online. Yeah, sorry. Sorry, I totally blanked, but the slides are back on. All right, so the PROTAC is able to destroy not just our normal wild type protein, which is the original protein. It can also destroy the subtly shape-shifted one, as well as the overexpressed one. And the PROTACs work in a really iterative fashion so that once that protein is destroyed, it can go back and get another one of the same protein and destroy that one too. So these are the major advantages of PROTACs. So whereas traditional drugs, the normal drugs that we take every day, they can only target about 15% of the different kinds of proteins that a cell produces. But a PROTAC can bind all the different kinds of proteins a cell produces. So it's effectively expanded our druggable space. So a drug usually works in a one-to-one manner where one drug is only able to bind and block one protein. But like I just said, a PROTAC works iteratively. It can bind and destroy multiple variants of that same protein. And the PROTAC's wonderful ability to overcome resistance is its key factor. So PROTACs have been used to treat drug-resistant cancers, and it's been incredibly successful. And the other real advantage of a PROTAC is that you need a much lower dose in order to do the same job. So you have less toxicity and you might have less off-targets, which are undesired effects. So what would we like to do with PROTACs in malaria? So we've got this amazing history of using antimalarials to treat malaria parasites. But all of these drugs, which used to be amazing, are now ineffective because we can't use them due to drug resistance. So what I would like to do and what my project is based on is to try and identify and create really good antimalarial PROTACs. So we've already got our antimalarial drugs. We just need to find compounds that will bind parasite taggers. And so that's what I'm doing at the moment, is to identify the right parasite tagger to use in renewing and re-energizing our antimalarial arsenal. So I think that's the end of my presentation. I'm really sorry. I completely blanked on the fact that that was up there. Yeah. So, but before I finish, I'd just really like to thank you. You know, I'm so amazed. Like I really enjoyed having a chat at my table. But you know, I wanted to tell you that over the last 5-6 years, when I've been working at WeHi, I use all of the different instruments that have been bought by the generous donations made by you all, and I never noticed it. Right. And just in this last week, while I was preparing my talk, I just made a count of like how often people use it. And it's amazing. They use it every single day. And, you know, medical science is a really collaborative effort. And it's not just collaboration among scientists, it's collaboration with funders and with supporters just like you. So thank you for your support and thanks for listening. Cheers.
Well, thank you very much, Danushka. I think it's quite amazing what's going on at WeHi. identifying the problem and the way they're going about resolving it with these new drugs. So I think it's very exciting, and we wish you the best to combat this problem. As I said earlier, 620,000 deaths a year is very significant. So, so thank you very much indeed. And I think as mentioned earlier, we hope to get a visit to Weehai organised later in the year. So we will advise when that visit is possible for those that might want to visit Weehai.